Okay, we're back. This is Bio 221. This is part 3 of Chapter 23 video, going over the respiratory system, and we're going to focus now on how we breathe, the mechanics of breathing, and we're going to start with the muscles of respiration. So there's two processes that occur when we breathe. You have inhale and you have exhale. So, and those require different muscle groups. Right? So your inhalation muscles, the muscles of inhalation include some of the obvious ones, right? Your diaphragm, right? Your diaphragm's like a big umbrella right underneath your rib cage, and when you inhale, it depresses, which enlarges the volume in your thoracic cavity. When you enlarge the volume, you decrease the pressure, and so air passively comes in when you contract the diaphragm. So your diaphragm is one. You also have your external intercostal muscles. Remember those guys from last semester? They kind of go diagonally through your ribs. They're basically spreading your ribs apart, helping to increase the volume of your thoracic cavity. So diaphragm, external intercostals. You also have the serratus anterior, other muscles that kind of come around from the back, helping pull open that rib cage. Your pectoralis muscles, again, helping to pull open and expand the rib cage. And your scalene muscles, attaching the clavicle, again, pulling your rib cage up and out. It's all about expanding and increasing the volume in your thoracic cavity. And then you have the opposite when we're exhaling. So you're inhaling, diaphragm and external intercostals are your major players. And then all of the assistants, the serratus, the scalenes, the pectoralis, those are going to help. But the first two, diaphragm, external intercostals, are the big guys. Then for exhalation, that's really a passive process. That's not really going to require any muscles contracting per se. All you just have to have the diaphragm relax. It pops back up into your thoracic cavity, decrease in the volume, increase in the pressure. Everything just pushes back out, right? But if I were to say right now, okay, I need you to blow out this candle, or breathe as hard as you can into this paper bag, right? That's going to force you to force air out, and then you're going to activate some muscles. You're going to activate your internal intercostals, and you're going to activate your abdominals, right? If you feel that, you're actually feeling your abdominals press in and your rib cage compress so that you can push that air out, right? So those are your muscles of respiration. Let's talk about one of the major concepts here, and this is a major concept in biology, and we talked about it a little bit in cardiovascular system, and it's the idea that that things move from areas of high to areas of low, right? High concentration, low concentration, high pressure, low pressure, right? And you're going to have the same thing happening here in the lungs. Air is going to move from areas of high pressure to areas of low pressure. And when we're talking about respiration, when we're talking about breathing, that is in comparison to the external environment, to atmospheric pressure. So our lungs have to have a different pressure inside of them than the atmosphere around us. And when that pressure is lower, air is going to come in. When that pressure is higher, air is going to go out. Right. So let's talk about some, let me look in your book. All that I just talked about right there was all on 825. And now we're getting into some of the pressure and volume. And there's a really good kind of sequence of diagrams there showing you the diaphragm and the way it depresses and inhalation loop on page 829, showing you how it's called the intra-alveolar pressure. That's the pressure within the alveoli. That's the pressure that we're concerned about. When I'm talking about the pressure inside the lungs has to be lower than atmospheric pressure, it's that intra-alveolar pressure that I'm talking about. So let's talk about some different volumes and things like that. Just like in our cardiovascular in our cardiovascular system, in our circulatory system, we had different formulas and names for things. You have the equivalent of what's called a cardiac output in respiratory terms. We have a respiration minute volume, which in other words is how much volume you exhale in 1 minute. Right? What was cardiac output? Cardiac output was stroke volume times heart rate, right? How much blood you're pumping and how many times you're pumping it. It's kind of the same thing here. How much are you exhaling in a minute? It's multiply, to get that, you take your frequency of breaths, right? How many times? It's kind of like your heart rate, but it's your respiration rate, and what we call your tidal volume. Your tidal volume is the amount of air you're exchanging right now without thinking about it. We're all sitting here, you're listening to me, maybe you're cleaning, maybe you're doing something else, or maybe you're sitting here taking notes. But you are breathing, and the breathing that you're doing, unless you're working out right now, is your tidal volume. Tidal volume is what you're doing at a resting level. That's your tidal volume. In and out. Think of the tides, right? Ebbing and flowing. That's what the air is doing in your lungs all day, every day, right? Unless you're working out, or unless I say, here, blow out this candle, or breathe into this paper bag really hard. You're just doing this tidal volume, in and out, in and out. And that's roughly 500 milliliters of air. No matter who you are, it's pretty much the same from person to person, about 500 milliliters of air. And that's broken down into two sections, because if you think about it, all the air that you're breathing in isn't going into the alveoli, right? The alveoli is the conducting, is the exchange membrane, right? That's where the actual magic happens in the lungs, right? That's where the air is going to be exchanged, the gas is going to be exchanged. Well, every single molecule of air you breathe in doesn't make it to the alveoli, right? There's going to be this kind of traffic jam in your respiratory system. Some of the air you breathe in only makes it to your trachea. Some of it only makes it to your primary bronchi. And that is called your anatomic dead space. Sounds kind of creepy. But it's just meaning there's no exchange happening there. There's no gas exchange taking place there. So when your tidal volume is 500 milliliters of air, really, and think about that, 500 milliliters. How many milliliters? This is 700 milliliters. This is my water bottle. So a little less than this is what you're breathing in and out every day. I think of like a liter bottle of Coke, and half of that, half of a liter is 500 milliliters. So anyways, 150 milliliters is that dead space, and 350, so the majority of it, in other words, is getting to your alveoli. 350 milliliters is getting to your alveoli. Do you have to know numbers? You should be familiar with them. And in most of my essays or case study questions, I'll give you an example, and I'll say, you know, this was the number, comma, which is high, right? So then you would kind of know that's a little high and be able to assume that, or you can always look it up on the case study homework questions, not on the exams, obviously. But you should be able to just remember 500 milliliters for tidal volume. That's pretty straightforward. So let's look at some things here. What do we want to talk about? Let's talk about some gas laws. That's pretty important. In order to understand how your lungs work, we have to understand a little bit of basic physics. So, I got my little pen out and my whiteboard. And let's talk gas laws. Let me move you back over here, get a little better angle. There we go. There's three main gas laws that apply in respiration. One is Boyle's law. Boyle, he's the guy that basically says, as your volume goes up, the pressure goes down, right? In other words, basic respiration, right? Increase the volume in your thoracic cavity by depressing that diaphragm, air is going to go in, vice versa, air is going to go out. So that's Boyle. Then you have this other guy, Dalton. Dalton basically said, and this is a totally new concept that we haven't talked about yet, he basically said the partial pressures of all of the gases in the air are equal to atmospheric pressure. So in other words, the major gases of the air are oxygen, carbon dioxide, nitrogen, water, right? You can take all of the partial pressures of those gases, and that's going to equal atmospheric pressure. So N2, partial pressure of nitrogen. Nitrogen is actually the most common gas in the air. You just breathe it in and breathe it right back out. We don't really do anything with it. Plus the partial pressure of O2, oxygen, plus the partial pressure of CO2, right, partial pressure of carbon dioxide, plus the partial pressure of water vapor. That all equals 760 millimeters of mercury, which is atmospheric pressure. So, what does that have to do with respiration? Well, we're going to start talking about partial pressures in our body and in our blood and how that plays a role. Remember, things go from areas of high to low. So areas of high pressure to areas of low pressure. This is going to make gas exchange possible at our capillaries, right? This is Dalton's law. And then the final guy, his name was Henry. Henry basically, he does what I call the soda can law. Can we see him on there? Henry. And he basically said gas under pressure can dissolve in a liquid, which in human body talk means that gas from the atmosphere can dissolve in our blood. Or the way I like to think about it, the soda can, right? You go to the soda can factory and they're pouring the soda in the cans, then how do they get all those bubbles in there, right? They pump that can full of carbon dioxide, and then some of that carbon dioxide dissolves into the soda, right, until equilibrium is reached. And then when you crack that soda bottle open, it all rushes back out, right, going back out into the air. So that was Henry that came up with that law, named it, whatever. Was noted for kind of observing that for the first time. So gas under pressure can go into a liquid, which is good because we can take oxygen out of the air and stick it in our blood, and that blood can circulate through our body. And then when the partial pressures of oxygen and carbon dioxide are different in different areas of our body, then we can exchange those gases, right, from high to low. And because we can inhale and exhale, we understand Boyle's law. So it's a good summary of all of the different gas laws and how they apply. I'm a big picture person. I like to understand how everything is and why it is so that I can understand the little stuff. So that is where I'll stop for this little video, and then we'll move on with some more complicated stuff in part 4. I think we'll be up to part 4. This is part 3. Alright, bye.